Now we want to do case 6 from chapter 9, which is on my website. Click on teaching, scroll down until you see PowerPoint 9 and case 6. Now case 6 is the sigma unknown version of case 3. So in case 6 you have to copy data from case 3 into case 6, and I've already done that. So here is chapter 9 case 6. The data is already in here. All 25 of you guys have different data because we have different samples. The sample size looks like it is 49. So I'm going to go ahead and enter that right here. Everybody has a unique set of numbers over here because we have unique samples of 49. Our sample of 49 observations is used to answer this question. An Atlanta restaurant has determined that profit is highest when the time between seating customers and clearing their table is 24 minutes. I'm going to make this phrase, the time between seating customers and clearing the table, I'm going to make that red and bold. And then I'm going to make the is bold. And I'm going to make the 24 bold and blue. Now the reason why I say that is because the null hypothesis, which always includes equals, is that statement, the time between seating customers and clearing their table. That is our population mean because we have a set of 49 observations on this variable. So the time between seating customers and clearing the table is 24. That's precisely this statement here. So another way to formulate the null hypothesis is the population mean mu minus 24 equals 0. So if the Greek gods of numbers tell us that mu is really 24, then 24 equals 24, correct? And 24 minus 24 equals 0. So these two statements here are equivalent statements. Now the alternative hypothesis is the opposite of the null. So the alternative hypothesis is the population mean mu, in this case the time between seating customers and clearing their table, is less than or greater than 24, i.e. the population mean is not equal to 24. Again, another way of restating the alternative hypothesis is mu minus 24 is less than or greater than 0. So for example, the Greek gods of numbers say that the population mean is really 20. Well, then the alternative statement here is true because 20 is less than 24. Over here, 20 minus 24 is a negative 4, and that is less than 0. Okay. Now, since this is a sigma unknown problem, we have to use a t-stat to conduct this test. And the t-stat is similar to the z-stat. We have the difference, we have the point estimate up here of that difference. X bar is in red because it is a point estimate of mu, the true population mean, which we'll never know. And then mu 0 is blue because it's the manufacturer's claim. In this case it is 24. So the manufacturer's claim is 24. Okay. So the t-stat, in summary, the t-stat is the ratio of the point estimate in this difference divided by the standard error down here. So we need three things to compute the test statistic, actually four. We need the sample mean, which we're going to compute right here. We have the manufacturer's claim of 24. And then we need the sample standard deviation, which we're going to square. Sample standard deviation squared is a sample variance. We're going to divide that by n. And so over here, we need the sample mean, which is denoted x bar. And x bar is computed by typing equal average and then highlighting the data over here, the sample mean is the average of the data in the sample. In our case, it is 25.8414. The sample standard deviation is denoted S, not sigma, but S, and it is found by typing equal stdev.s, and we use .s because we're talking about a sample standard deviation, so we need .s for sample. If we had all the data, all the observations from the population, we'd use .p, but we need .s because we have a sample of data. And then we highlight the data, the observations of the variable, and we get 5.4255. Now every one of us is going to have a different sample mean. Mine is 25.84, and I bet most of you have a number right around 25, 26. So one or two people might have one that's way above and way below, which would trace out a normal distribution. And we get a pile up. The hump of that normal distribution is at the true population mean, which is probably 25 to 26. The same thing's kind of going on with the sample standard deviation. We're all going to have different numbers. Some of you are going to be below 5, some are going to be above 5, but we're all going to be really close to a number that we can never know, the true population standard deviation. But we're going to have a pile up at that true population standard deviation. We calculated the standard error in Chapter 8 by taking the sample standard deviation and dividing by the square root of the sample size. Whoops, I gotta spell square root correct, which is 0.775065391. Now, if you look at the t-stat, it's a little different. The t-stat, to get the standard error in the t-stat, you take the square root of the sample standard deviation squared, aka the sample variance, you divide that by 49. Either way you get the same number. Okay? You get the same number. Both of these are identical numbers. So we'll just leave it as the method that we use in Chapter 8. We'll calculate the standard error here just like we did in Chapter 8. Now the numerator of the t-stat with the denominator calculated down here, the numerator of the t-stat is the difference in the sample mean and the hypothesized value of 24. And it's 1.8414. And as I've said many times before, the probability that the sample mean equals your true or your company's claim, the probability that those two things are equal is 0, because there's 124 on the number line and there's infinite many numbers a sample mean can take on. In my case, it takes on the value 28.8414. So the sample mean is the point estimate of the population mean. The point estimate of this difference is the difference between 25.84 and 24. So that's what we call that the point estimate of the difference. Now the t-stat is equal to the point estimate of the difference between the sample mean, or the estimate for the population mean, and the claim, divided by the standard error. And our t-stat is equal to 2.376. Now we got to compare that to the critical values. Going back to the alternative hypothesis here, the alternative hypothesis says we have a lower tail test and an upper tail test. In other words, we have two tails to this test. So what we have to do is we have to take the significance level. We have to take the significance level here, and the significance level was, in the problem, 10%. So alpha equals 0.1, that's our significance level. We have to divide the significance level by 2 because we have a two-tailed test according to the alternative hypothesis, which means alpha divided by 2 is 0.05. and that is our row. That's the column of the t-table. And the t-table is where we get the critical value. We have to compare the t-stat to two t critical values, and we're going to find the critical values in column 0.05 of the t-table. The row is found in the degrees of freedom. The degrees of freedom, in other words, the degrees of freedom here, 48, because our sample size is 49. The degrees of freedom is 48. That's the row in which we find the t critical value. So let's go back to my website and click on the t table. I'm going to blow this up a little bit, zoom in a little bit, so we can see it better. We're in column 0.05, right? Column 0.05 of the t table, column 0.05 and row 48. And so the t critical value is 1.677. So just double check 48 and 0.05. 48 and 0.05. So the t critical value is 1.677. Okay. Now, again, we have a two-tailed test, which means we need a negative t critical value and a positive critical value. So I have the negative t critical value here, and then I have the positive t critical value here. Okay, I think I'm going to rearrange this just a little bit. Put that up here, put that down there, and then put that right there. So if the test statistic is in between these two critical values, we can say that this difference is insignificant. The t-stat is insignificant. So when the t-stat is insignificant, then we have evidence in support of the null hypothesis. Now the intuition is this: 0 is in between these two values, and 0 is the right hand side of this equation. Mu minus 24 equals 0. 0 is in between these two values. So if the t-stat were in between these two values, we have an insignificant difference, and the data would support the null hypothesis. However, that's not the case here. The t-stat is not in this interval. The t-stat is actually above the upper limit of that interval, which supports the alternative hypothesis. So our t-stat is not in this interval. Our difference is not insignificant. So our difference is significant. And because the t-stat is positive, our difference is both positive and significant. So we're going to reject the null hypothesis. So we can reject the null hypothesis at 5% significance. That's what we want to write. Now if we are telling this to a person who has very little statistics training, they're not going to know what we mean by that. So we have to write this in a way that a person without statistical knowledge or training can understand it. So when you reject the null hypothesis, what are you saying? You are actually saying the alternative is true. And where did we find the alternative hypothesis? Well, the problem contains the null hypothesis. That shaded area there, that shaded phrase, is the null hypothesis. How do we make that the alternative hypothesis? Well, the alternative hypothesis would be the time between seating customers and clearing their table is not 24 minutes. Okay, so I have copied and pasted the null hypothesis from the problem into this cell here. To make it the alternative hypothesis, I have to type not. So now we have the alternative hypothesis. The time between seating customers and clearing the table is not 24 minutes. And since we can reject the null hypothesis at 5% significance, we can say we can conclude that the time between seating customers and clearing the table is not 24 minutes. And that concludes case 6 from chapter 9.